name is Hsi-sheng Goan. If you can read it, okay. It's Chinese character. Yeah. All right. I'm from a totally, completely different research field. I'm actually in quantum computing, or quantum information science. Has a little bit to do with biomolecular physics or biochemistry. But I guess I can give you some different perspective on what people mean by quantum decoherence. And Ross said to make it simple, so I really want to make it simple. Okay. I hope it's not too simple.
Yeah. Don't make it too simple.
Okay. Okay. So when is quantum dynamics necessary or important? Here I will not go into the debate of when it's necessary for biomolecule functionality or something like that. I'll just say when is it important. Usually, quantum dynamics is important when there's a good isolation. So your system is well isolated. A small size, small mass, a low temperature, a short time. But remember, all these they are all relative scales, depending on the system and what is your environment around your system. Okay. For example, this good isolation, small mass, low temperature, short time, this all has something to do with the decoherence time. So the decoherence time is a time scale when the quantum superposition property disappears. So when this superposition property disappears, then you no longer have the quantum mechanical property of your system. No longer have this property. So after that time scale, then you can perhaps forget about quantum mechanics then. So all these are all the relative time scale here. So coherence. So I borrowed several slides, actually many, from the Liu Renbao lecture. Okay, I find it's very heuristic. I hope. So the first coherence is a constant phase difference in two or more wave or times. So what is that? Oops. So if you see this muching, they are muching together. So it's coherence. So decoherence, someone is out of phase.
Yes.
Yeah. So when someone is out of phase, usually often it's because of entanglement with the environment. So what is the entanglement? Perhaps I will give you some. So I'll give you something about what is entanglement later. But just remember, it's just entangled. Okay. So this is out of phase. So what happened to the decoherence? Decoherence is entanglement with some environment. But then sometimes this guy is out of phase, and sometimes the next guy is out of phase. It's randomly of time. Okay. So then that will make, so for each individual thing, so for each individual run, some of them are out of phase, but it's not always this guy, okay? So that's the important concept of fluctuation. And recohere, okay, by a little bit controlled, then, so that's in quantum computing field, we're actually working about how to fight against decoherence, because we want to build some quantum information processing device which operates quantum mechanically. So that means we need to have coherence. All right, so to make it simple, let's look at the double slit experiment. Okay, so if it's a bullet, so usually you will not find any interference pattern. So usually if you double slit, so the bullet went through, so there's a peak here, so there's overall like that. So if it is sound wave, so then it's wave, so then you find the interference pattern. So usually we understand this is using the wave property. So from the wave property, from the interference, you actually can find the interference pattern like this. Not for just sound wave, the cross wave, or also for EM wave, electromagnetic wave, for laser or something. Usually people just explain this interference like that. That's perfectly fine for wave. But what happens if it is the electron? So electron now consider a particle. But now, if electron is a particle, but also there is a de Broglie wave. So when the diploid wavelength is comparable to the width of your slit, then you will see diffraction interference pattern again, even for the electron. So what happens if I put a detection or eyes here to see which path the electron goes through the double slit? Then I no longer have the interference pattern. Okay. So this is something strange. But if now I can fire the electron one by one, what happens? What can I see? What will I see? So now if you can fire electron one by one, something like that, one goes in, then there is 1 point there, 1 point there, 1 point there. So what happens? Wow. If we wait until there is a diffraction interference pattern, we will take 20 minutes. So let's go fast. Okay. So even with electron going through the double slit one by one, but after many electrons passing through, you will see the interference pattern. So the thing is, the photon or electron interfere with itself. Okay? So interference is no wonder. The wonder is that a particle interfere and then it interfere with itself. So even one particle going one by one, they interfere with itself and give you the, when you have ensemble particle like that, then you give you the interference pattern. Okay. So each individual run is very stochastic, but the ensemble property you can predict is like an interference pattern. So and then again, superposition is not a mixture of two pathways. So you may wonder how this guy can pass through this. Okay. So if the photon passing through two slits or electron passes two slits simultaneously, if which way information is on there, then there is no interference. So what happens? So if we know, if you block this slit first, and let the electron going through, and then open this one and block this one again, then again you will see the one by one, but it takes time, so you will no longer see the interference pattern. What happens if I don't block? This is the which way is pre-select, and this is which pathway is recorded only. Okay, but the electron still passing through. Again, you will see there's no interference pattern for these things if you know which way information. So what happens if now I put instead of the I can measure which way, I just put a random phase shift. If you put a random phase shift, what happens to this? For each electron, it looks like the stochastic, but the ensemble property of this, still, there's no interference pattern. Of course, here, I'm assuming this random phase is strong enough to destroy the interference pattern. But usually, that depends on how random. So summary is like this, okay? So for a single slit, you see this. For double slit, you see interference pattern. But with a random phase on this, for example, the second pathway, there's a random phase, then you will see this with this random phase. And this random phase will smear out the interference. When the random phase is strong enough, then the interference pattern will smear out completely, then you will no longer have the interference. Okay, so that's the concept of the electron here, it actually acts as a quantum mechanical particle. So when you have when you know which way to go, then you actually corrupt the wave function of this single electron to just one single pathway. So because of that, so you no longer have the interference pattern. So let me now just give you some 1 minute on what is entanglement. Okay. So for example, for superposition states, so for example, let's say 0 is ground state, 1 is the excited state, or 0 is the spin up state, or spin down state, or 1 is spin up state, something like that. So if there's an energy difference between them, so then, for example, as a function of time, this state will evolve, something like that. If this energy is constant in time, then you will see the oscillation like that. But now, what happens if you have some phase in the energy? If your energy shift a little bit, jiggling a little bit, so then you have a random phase with time, then you will see something like this. If each time the jiggling are different, if you do the ensemble of these particles, then you will see a decay. Okay? So for each individual run, it looks like that. It's not decay. But if you do the ensemble, then it looks like a decay. So what happens? Why do we have this random phase? Because now the atom is no longer isolated. There's some environment provide this jiggling. So thermal environment or whatever give you this fluctuation. So that will give you, and then if you no longer have this information, then you will have the decoherence if you do the ensemble of your system. Okay, what is entanglement? Entanglement is the property between subsystem of a composite system. Okay. So for example, I have a composite system consists of A and B. So for example, A is in 0 state. And for example, in this state, I can rewrite this as a tensor product of A is in 0 state and B is in this superposition state. So when I can write A is in some state and B is in some state, I define this as separate state. So that means I can tell you the A particle is in some state, B particle is another state. So what is entanglement state? Entangled state is the state which cannot be written as a tensor product of the subsystems. So for example, this state, this is a spin singlet state. For example, you can say this spin up, down, down, up, this spin singlet state. Spin singlet state, you cannot say the A is in what state and B is in what state. No longer you can say A is in what state or B in what state. So it's non-separable state. So then this is what we call entangled. Okay? So you only can say the joint state of the two particles rather than A is in what state, B is in what state. So that's entangled. So why entanglement is important? Entanglement is important to understand the decoherence as well. So for example, if you take the separate state, because we usually, when we talk about decoherence, we usually have a system of interest and the environment. Okay, other environment. So we can divide the system as one subsystem and the environment as the other subsystem. So when these two are separable, so for example like this fire. So usually when we talk about the system of interest, we trace over the degree of freedom of the environment to see the average effect of the environment on the system. So usually we will do the procedure that means partial trace over some subsystem variable. So for example here, if I trace over the A subsystem variable, the A subsystem, for this separate state, I write in density matrix form. Then this is in pure state. If they are separable, that means I just trace out this. So what I left with is this. But if these AB are entangled together, if I do a partial trace on the A, then I find this state, when I do the partial trace on A, I only get a mixed state. It's no longer pure. So that means I lost some information. When they are entangled, if I trace out the environment degree of freedom, I lost some information about the pure state to begin with. So that's how, when you do the average on some subsystem, then you lose information, then you have the decoherence. So this is important when we have when system and environment are entangled together. Then you trace over the environment degree of freedom, this the decoherence. Okay, so what is superposition state? It's something like this. Sometimes 0, sometimes 1. Okay, 0 or 1, I don't know. But when you measure it, then you know it's 0 or 1. Okay, so decoherence. Wow. Decoherence is a process by which a quantum superposition state decay into a classical statistical mixture of the state. So that means from the superposition to a classical mixture. In the system environment model, usually we understand the decoherence, and most people think it's because of the environment. The decoherence is caused by the interaction between the system and the environment. The system or the bus or environment evolve under the total Hamiltonian, they become entangled. When they entangle, then you trace out the environment degree of freedom. Then the reduced density matrix of the system of interest is no longer pure. And the system say have decohere. Okay. And here is entanglement sharing. So entanglement has something to do with decoherence too. Okay. So for example, if I have such three subsystems SB, B1, and B2. So if there are some interaction between them. So if B1 and B2 are strongly entangled, then so if B1 and B2 maintain appreciable entanglement, then there is a restriction on the entanglement between the central spin and the B1 and B2. So if these two have strong entanglement, so then there's the entanglement between these two and these two, there's a restriction between them. So once there's a restriction between the entanglement, then when you trace out B1 and B2 degree of freedom, then there is a restriction on the amount that S may decohere. Because if it's strongly entangled, then when you trace out this system, then you release the strong decoherence, something like that. All right, so we talk about the decoherence. Now let's talk about the oscillator bath and spin bath. So generally, when we model the environment, in most of the case, we use the oscillator bath. Oscillator bath will describe the delocalized environment modes, like electron, photon, magnon, or something like that. The spin bath usually describes the localized mode, so like nuclear paramagnetic spins, or charge trap, or defect, or some localized modes. So they are usually, and also now we also have, rather than the oscillator bath, we also have the free electron bath, like the electron now. Well, although it's in this category, but electron is fermion, then photon is boson. They have different statistics. Okay, then the spin boson model is well, yesterday Joe talked about the spin boson model. I probably briefly mentioned it a little bit here, and so that is a two-level system, something like a spin or interacting with an oscillator bath. The spin boson model. Central spin model is like there's a central spin interacting with the spin bath, or quantum Brownian motion model. This is also a popular model to study the decoherence. Is a quantum particle interacting through position or momentum with an oscillator bath. But usually the interaction between the central system and the bath may often strong, and the correlation time of the bath may sometimes comparable to the system response time. Then, when this happens, we need to consider non-Markovian behavior. Okay, so I just quickly.
2 minutes.
Oh, 2 minutes. Wow. So then I will skip this then, because Joe talked about this yesterday. So I probably skip this. I just mentioned that in our community, in superconducting, in our quantum computing community, we are looking for systems which would exhibit quantum mechanical property. So we are talking about, for example, yesterday, if it is something in a biosystem, because of the weight and the heart and all those things, so it would not be a good place for us to look for quantum mechanical property. So for example, for the superconducting quantum bits, usually the decoherence time, when experimentally they determine this, in this device, the decoherence time is roughly now is in microsecond region. Okay. So it's much longer than the femtosecond, picosecond, and that. So that means within the microsecond, you still can see the superposition state. Okay, you can still see the coherence oscillation between the two states. Okay, so I think I will skip this. I'll skip also this. I just mentioned briefly, since there's 1 minute left. So I just mentioned briefly some quantum Brownian motion model. Some quantum Brownian motion model is oscillator fed, and I have a particle. Particle is in some potential. I assuming it's also in the harmonic oscillator potential like this. And the interaction between this Qn is the bus variable, X is the system variable, coordinate variable. So if the interaction is like that, I can find the quantum master equation. The quantum master equation has several components here. So when there is no environment, I only have this, the density matrix, equation of motion for the density matrix will only be HS system, and the rho is only this. But when there is an environment, I add several components into this evolution equation for your density matrix. One is, for example, this renormalization of your frequency. That's renormalization of your energy. And also this is damping for your oscillator. The oscillator is no longer, the evolution is no longer unitary. This is damping here. And also here, there's a decoherence. This is diffusion. And this is also another diffusion term. The diffusion will give you, for example, this term give you the decoherence term. Because when you write a rho in this is in operator form. If you write in the coordinate form, x and x prime representation. So that means when x and x prime are different, this term decay very quickly. So that gives you the decoherence in position representation. Well, these all the time dependent coefficients, I think I spent too much time previously. So that's one thing. So that's a model. When you couple to a bosonic bath, then you have that kind of master equation. But now, if you have oscillator coupling to a fermion bath, like a tunneling barrier like this, if you have one electron can tunnel through here, the electron and this oscillator has interaction. The interaction is also through the coordinate of the system X. Then you also can look, then the resultant master equation almost have the same form, but with different coefficient. The coefficient, of course, now it's determined by the, for example, the voltage across this, and also the mass and the coupling constant, and something like that. But you still have very much the similar form. And also, if you have rather than coupled to a single electron transistor rather than just a tunneling barrier, then you can also find, well, the Hamiltonian look like that. But if you see this, it's also through the coordinates, the coupling through the A dagger plus A is the X component. So then you also find the resultant master can look at the same form. So, okay, well, I guess I don't have time to talk about what I have done. So I will go to the summary now. All right. So the summary, I think the take-home message would be, okay, there are some important properties like the Bass spectral density, the operator form, and the strength of the system Bass coupling. But this is one of the messages. While the detailed constituents or property of the Bass are important to determine the relaxation and the decoherence rate, the form of master equation of the reduced density of the system may look the same for different Bass. For example, for bosonic bar or fermion bar, if the system operator in the system bus coupling is the same. Also, the dynamic of single quantum system in a single run experiment is usually quite different from their ensemble counterpart. All right, thank you for your attention.
Okay, we have time for a couple of quick ones. Ben?
So when you define your entangled, when you write the definition of entanglement, you're assuming you have distinguishable particles. So
well, there's a particle 1, particle 2. It's right. Like a spin up and spin down, right?
What about having indistinguishable particles?
Well, they are also indistinguishable particles, but then you have, for example, here I'm saying that. Yeah, you mean you need to symmetrize? Yeah. Well, there's a spin part and there's an orbital part too. Okay, so when I talk about this, I generally assuming, okay, if A and B are different particle or different subsystem, then if you can write it in that form. But in general, if it is in the same, well, indistinguished particle, then if you need to totally symmetrize it or whatever, then they probably in some entangled state. What I mean is, as long as you cannot say the A is in some state and B is in some state, then that's an entangled state.
Jeff, last question.
Your slides where you're talking about entanglement and tracing over subsets of the variables and all that, we have similar slides in our undergraduate lectures, but the title on the top would be Breakdown of the Born-Oppenheimer Approximation.
Okay.
Is there anything in what you've described that isn't just simply Breakdown of the Born-Oppenheimer Approximation?
Well, I think it's a different point of view to understand certain things. Okay. Yeah, so I...
Just trying to get rid of the nuclear degrees of freedom and look at the electronic ones.
Well, yeah, well, you can say that well, I don't know exactly. Perhaps that's some kind of approximation already, because you trace out some degree of freedom already. Yeah, so I would agree that.
Okay, well, I think we'll stop there, and thank Hsi-sheng for his...